Chapter 6 about exponential functions and their derivatives. So an exponential function, f of x, equals some base raised to an exponent. So that exponent is the variable, it's what changes and what grows. And our base could change too. So an example is like 2 raised to x. Could be 3 raised to x. Those are examples of exponential functions. And then we have our exponential rules, or our normal rules that we kind of come across. So we have a x plus y. Well, when do we add exponents? Well, we add exponents when we're multiplying by the same base. We add exponents, right? Or when we divide by the same base, what do we do with our exponents? We subtract them, right? So when we divide by the same base, we subtract exponents. When we raise powers to powers, so powers to powers, raise a power to a power, we multiply those. And then finally, when I have a product being raised to a power, only a product, so not addition, only multiplication in here, that means I can take that power and bring it to both numbers in there. So a to the x, b to the x. Okay, so those are your rules of exponents that we normally come across. Now let's go ahead and look at the limits of exponents. So the limits of exponents, like I said, here's our function, normal exponential function. If I'm going to take the limit of this, I'm taking the limit as x goes to infinity of a raised to x. Now if our a, our base, is greater than 1, then this will just go to infinity. Or if I take the limit as I go towards negative infinity of a raised to x, then that's going to go to 0. So as this gets, x gets smaller and smaller and smaller, because that negative is going to flip the fraction, right? And so it's just going to get closer and closer to 0. If a is between 0 and 1, then when I take the limits of these, a of x, then here I'm going to go towards 0, because this is a fraction, and I'll raise it to a fraction, it's just a root, right? So if I have any type of fraction in here, that's just going to get closer and closer to 0. And then if I go towards negative infinity, that negative again is going to flip that. And so that is going to go to infinity. So here's an example. So 2 raised to, my a, this a is 1/2. So between, a is between 0 and 1. And so as I get bigger and bigger numbers in here, right, this is just going to be 1/2 times 1/2 times 1/2 times 1/2 times 1/2. So that's just getting smaller and smaller and smaller and going towards 0. If I have 1/2 and that's being raised to a negative 100, well, that's going to flip it, and it's going to become 2 to the positive 100, and so that's just going to go to infinity. All right, so let's go take a look at the derivatives of exponential functions. So if I have an exponential function, f of x equals a raised to x, and we want to take the derivative of this, we can do it by, because we don't know how to do it yet, right? So we have to go back to the limit as the limit of the difference quotient, so as h goes to 0, well, that's taking f, oops, not an equal sign there, f of x plus h minus f of x all over h, right? So I plug in my x plus h, so that would be x, or a raised to x plus h minus a raised to x all over h. And then I can go ahead and just rewrite using, when I add my exponents, that means I am multiplying by the same base, so that's a raised to x times a raised to h minus a raised to x all over h. Again, and taking the limit as h goes to 0. And then I can rewrite that. I can factor out the a raised to x. So I have this over h. Again, I'm taking the limit as h goes to 0. And so since a to the x does not depend on h going to 0, there's no h in this, I can go ahead and bring that out front, and I have a to the x times the limit as h goes to 0 of a to the h minus 1 all over h. And so as we look at this, we want to figure out what the f prime of 0 is, so the derivative at 0. So there, when I plug in 0 in for my x, that a to the x would be a to the 0, which is just 1. And this would be taking the limit as h goes to 0 of a, and there's no x in here, right? So since there's no x in this part, then I just have f prime of 0 equals 1 times the limit, so it's just the limit. So h goes to 0, a of h minus 1 all over h, right? So, and we know since this right here equals the derivative of 0, then it also right here equals the derivative of 0. So we can say that the derivative of f of x, our exponential, is equal to the derivative evaluated at 0 times a to the x. So what this tells us is two things. One thing, the derivative at 0 is true, as well as it's also differentiable. I can find the derivative anywhere. So I can find the derivative anywhere of my function. Notice the derivative of my function contains my function and then just times whatever the derivative at 0 is. So now we need to figure out just what that derivative of 0 is. So if you investigate a little bit, you put some numbers in for a. So the derivative of 0 is this. So if I put in some numbers for a, like I put in 2, and I evaluate this as taking the limit as h gets closer and closer to 0. So as I put in 2, I get closer and closer to this number, 0.69. As I take the limit as h goes to 0 of plugging in 3 for my a, that number gets closer and closer to 1.10. And it gets closer and closer, and if you look at more and plug in more numbers, 3 and 2, this number eventually approaches f prime of 0, eventually approaches 1. So it approaches 1, and I'm sure you can look up the proof on that. So this part, a raised to h minus 1 all over h, goes to 1, so that means that our derivative, this there would be 1 then, so 1 times a raised to x equals a to the x. So the derivative is a raised to x. Well, that's what we started with, so that's pretty cool. So then we have these derivatives. The derivative of e to the x is e to the x. And then if we want to take some derivative, say, of something that's not raised to e to the x, exactly, e raised to tan x, well, then I just use my my chain rule. So I take the derivative of e, which is e to the x, and I times that by the derivative of tan x, which is secant squared. So I have e, I leave this the same as what it was, which is tan x, so e to the tan x times by the derivative of tan x, which is secant squared x. So there's the derivative of this, so y prime. So in general, if you're taking e raised to anything besides x, the derivative of that is just going to be e raised to whatever that is. I leave the inside the same, and then I times that by the derivative of u. So the derivative of u. Okay, so that's how you do those exponentials. Here's another one. Again, it's more complicated. Here we got to come back to the exponential rules, or derivative rules that we've that we've done before. Okay, so here is product rule. So product rule, I have f, I have g, and I have to take f times the derivative g plus, or maybe that's switched around, I can't quite remember, and then g prime times f. So I take the derivative of f, and I take the derivative of g. So both of these, when I take the derivatives of f, that's going to be chain rule. And same thing with g. G prime will also be chain rule, because I got a sign inside a function. Okay, so for this one, the derivative of f is, I leave that the same, and then I times it by the derivative of the inside, which is the derivative of negative 4x, which is just negative 4. So derivative of f is negative 4e raised to the negative 4x, where the derivative of sine to the 5x, well, sine to the 5x, the derivative of sine is cosine. So cosine to the 5x. And then I go ahead and times that by the derivative of the inside, which derivative of 5x was just 5. So I get 5 cosine 5x. And now I can do chain rule, or I can do product rule, because I'm multiplying here, so I'm adding these two. So that's negative 4e raised to the negative 4x times by what normal g is, which is sine 5x. And then I'm adding, taking the derivative of g and timesing it by f. So f is e to the negative 4x, times that by the derivative of g, which is 5. So I'm going to put the 5 way out front here. Sine 5x, or cosine 5x, sorry. That's the derivative of g. Okay, so it kind of looks like that. All right. And then here's a couple of exponential limits on e. Limit as x goes to negative infinity of e to the x, that's going to go to 0, because it's just like this e is bigger than 1. So it's going to have the same rules apply. Limit as x goes to positive infinity of e to the x, that's going to go to infinity. So sometimes you might have to simplify and use different things, like say the limit as x goes to infinity, if I'm evaluating this limit of e raised to the 2x over e to the 2x plus 1. And then I can go ahead and just rewrite this and simplify and just divide the numerator and denominator by e to the 2x. So if I divide this by e to the 2x and divide this by e to the 2x, then I can go ahead and simplify this. All right, so this would be the limit as x goes to infinity of 1 over 1 plus 1 over e to the 2x. And I can go ahead and change that, use my exponent rules. 1 over 1 plus e to the negative 2x. And so I can rewrite that, and then I can distribute the limit. I just take the limit of the top, which is just going to be 1, take the limit of the bottom, which is just going to be 1, plus the limit of this. So I have 1 over 1 plus the limit as x goes to infinity of e to the negative 2x. And as that gets bigger and bigger and bigger, right, because this negative right here, right, because that negative right here, this is just going to have a negative exponent, which is going to flip it, and it's going to go to 0. So this just equals 1. Okay, so there you go. All right, last one is the integral. Well, if the derivative of e to the x is e to the x, that means the integral of e to the x is going to be e to the x. You just have to add a c for the definite integral, or for the indefinite integral. For the definite integral, you're going to have to plug in your a and plug in your b, right? But yeah, that's the integral of it, so it's pretty simple. So the integral of x squared e to the x. If I'm taking the integral of this, then all I have to do is just, here I'm going to have to do chain rule, because I have this right here. So if I let u just equal x, oh sorry, this is actually x cubed. That's actually an x cubed. So I'm going to let u equal this, so u is going to equal x cubed. So that means the derivative of that is 3x squared dx. So then I can substitute this, the integral x squared e to the u dx. I'm going to put the x squared dx together because that's what I need to solve for here, right? So if I divide this by 3, there I have my x squared dx. So that's du over 3. That's what this equals, right? And then I can bring that 1/3 out front. The integral of e to the u, which is e to the u. So that means I can put my u back in, x cubed, and then I can just add c at the end. So there's the answer to that. All right, under 16 minutes. That's pretty good.